Welcome back to The Deep Dive, the show where we take a monumental stack of engineering reports, strategic blueprints, and competitive analyses and distill them into the knowledge you need fast. Today, we're peeling back the sheet metal on the fastest growing and, I think, the most constrained segment of the global electric vehicle market, the micro low-speed pure electric passenger vehicle, or LSEV. Now, these aren't just golf carts. We're talking about highly engineered urban runabouts, things like the European L70 category, the China 800 class, and of course, the incredibly sophisticated Japanese K cars. You know, the global EV market is polarizing dramatically. We spend so much time talking about the high performance end, the Teslas, the Porsches, but the real engineering challenge, the true engineering gambit, is right here in the micro segment.
It really is.
Why?
Yeah.
Because you have to fit essential safety, mandatory compliance, and expected comfort into a system that's defined by three really non-negotiable constraints. Almost no packaging space, a razor-thin cost budget, and an incredibly sensitive small energy reserve.
And every single lot that's drawn from that battery by an auxiliary system, like heating or cooling, it's not just a comfort feature, it's a strategic liability. It directly impacts your range.
That's the core conflict then.
That is the core conflict we face. And as chief systems engineers, our mission today is to move past all the hype and provide the strategic roadmap, the technical blueprint that you'd need to build a world-class thermal management system, or TMS, for this new vehicle. We aren't just, designing components, we are developing the definitive statement of requirements, the SOR.
And the SOR is basically the Bible for the engineering team.
It's the binding contract. It's the contract between the vehicle architecture and the engineering delivery team. It's what ensures you get global compliance, you maximize your efficiency, and crucially, you maintain that aggressive cost competitiveness.
So we're breaking down this engineering blueprint into four critical pillars today. First, we'll look at the regulatory requirements that define the absolute safety baseline.
The non-negotiables.
Exactly. Second, the crucial strategic lessons you can learn from benchmarking competitors and their essential trade-offs.
What did they get right? And more importantly, what did they have to give up?
Third, we'll define the optimal hybrid architecture that tries to balance that cost and performance. And finally, we'll get into the details, the quantifiable engineering specifications, the hard numbers that the suppliers absolutely have to meet.
Okay, let's start with that regulatory floor, because before we can even think about specifying a single component, we need the fundamental rules of the game.
Absolutely.
Our source material really highlights the period between, say, 2020 and 2025 saw this tectonic shift in EV safety standards. It moved the entire industry from simple warning mechanisms to, complex active control systems.
That is the fundamental strategic shift. And while, Europe's UNS R100 standard is still central, you have to look to China because the Chinese GB 380.0381 standard has rapidly become the de facto global pace setter that's forcing higher safety standards everywhere, even in export markets.
So that's the foundation. That is the foundation upon which our entire safety system has to be built.
And there's one high-stakes constraint in there, the one that really defines whether we're going to be using liquid or air cooling. It's buried in the updated Chinese standard, GB 38031-2025. This is what you call the life or death constraint.
Precisely. The new standard mandates that the battery system must guarantee, and this is the exact wording, no fire, no explosion, for a minimum of 2 hours following a single-cell thermal runaway event.
2 hours. That's incredible.
It is. To really appreciate the scale of this change, the previous 2020 standard only required the system to give occupants a 5-minute warning before a thermal runaway happened.
So you had 5 minutes to pull over and get out of the car.
You had 5 minutes to get out. That's it. Now, we are talking about 2 hours of guaranteed suppression after the event has already started.
That is a massive window. It completely shifts the design goal from just allowing escape to actively containing or suppressing a catastrophe.
It does.
So what does that specifically imply for the engineering of a micro EV's battery, given you have almost no space to work with?
Well, it immediately invalidates simple passive air cooling for any serious LSEV, just straight out the window.
Why?
Air has an inherently low specific heat capacity. It's also got poor thermal conductivity compared to a liquid. So when one cell goes into runaway, and we're talking about an enormous sudden blast of heat air, just can't export that heat mass quickly enough to stop it from propagating to the next cell and then the next.
So you get a chain reaction.
A chain reaction.
Yeah.
And you can't meet that 2-hour suppression window. Therefore, our SRR must mandate one of two things. Either active, high-efficiency heat export, which, let's be honest, almost certainly requires liquid cooling.
Mm.
Or you have to include extreme thermal resistance buffer materials.
Things like what?
Things like phase change material, PCM, or aerogel. Materials specifically designed to absorb or halt that initial heat front right in its tracks.
So liquid cooling isn't just about, optimizing your range anymore. It's now a mandatory safety feature driven entirely by regulation.
It is the most robust and, frankly, the most cost-effective way to achieve that 2-hour standard for a mass-market vehicle. And it's
Right.
not just thermal. The new GB standard also imposes structural demands.
Okay.
New testing protocols include these rigorous battery bottom impact resistance tests and safety checks after fast charging. This is crucial for micro EVs because that cooling plate, the one designed for heat transfer, now has to serve a second purpose.
It has to be structural.
It has to be structural, a protective function against road debris or, heaven forbid, a low-speed collision. So our SOR has to define the material strength and the mounting integrity of that cold plate with this dual purpose in mind.
And the standard even reaches into the cabin, bringing in things like fluid dynamics.
The rule strictly limits smoke and toxic fume ingress into the passenger cabin during a thermal event, which
It's
not just common sense. It requires some pretty high-level engineering. The SRR must mandate the use of sophisticated fluid dynamics simulation, CFD, to precisely design the venting pathways for those high-pressure, hot exhaust gases. You have to make sure those vents are strategically located to direct all that nasty stuff safely away from the HVAC air intake.
so you don't accidentally suck it back into the car.
Exactly. You can't have it being drawn back into the vehicle interior. It's a non-negotiable safety element that demands integration between the BMS team, the structural team, and our thermal team.
Okay, let's shift focus over to Europe, where the constraints feel a bit more environmental and comfort-driven. Let's start with the F-gas regulation.
Right. So the F-gas regulation, that's EU No. 517/2014, it's all about reducing high global warming potential, or GWP, refrigerants. R134A, which was a really common legacy refrigerant, has a GWP of 1430.
Which is very high.
Very high. It's being phased out. So for our LSEVs SOR, the compliant choice is R1234BEF. It has a GWP of less than 1. This decision is mandatory. It's non-negotiable if you want to sell in the EU.
I know R12340 solves the GWP problem, but I also know it introduces a different, pretty high-stakes safety problem. It's mildly flammable.
That's the strategic trade-off. R1234F is classified as A2L. Now, since the HVAC evaporator that contains this refrigerant is located near or sometimes inside the cabin, and LSEVs are, let's face it, often poorly sealed, the SOR must require an ISO 26262 compliant functional safety protocol.
Well, what does that mean in hardware terms?
It means mandating high-reliability refrigerant leakage sensors right there in the cabin loop. If a leak is detected, the system has to immediately trigger mandatory full fresh air ventilation to sweep out any potential concentration of flammable gas. We have to define that component and its control logic explicitly in the SOR safety section.
Then there's the massive energy drain that's imposed by winter requirements. I'm thinking specifically of defrosting. For a tiny micro EV, this single factor can cripple your winter range.
It is the primary power requirement driver in cold regions, without a doubt. The EU Regulation 67/2010 mandates very specific windshield defrosting performance. The system has to achieve 80% clearance of defined visibility areas within just 20 minutes.
And that's under some pretty severe conditions.
It is. It's often tested at a negative 18 degrees C cold soak.
Meeting 18 degrees C in 20 minutes demands a huge amount of instantaneous power. So this isn't just a comfort issue for the driver, it's a regulatory mandate that directly dictates the size of our heating system.
Absolutely. This single regulatory requirement critically dictates the minimum size and power of the heating system, which is almost always a high-voltage positive temperature coefficient, or a PTC heater. That minimum power output is not something we can just arbitrarily choose. It has to be the output of thermal modeling that's validated against that specific regulatory test case.
Okay, finally, let's cover North America. I know a lot of LSEVs operate under the less strict NEV or neighborhood electric vehicle classification, but if a manufacturer wants broader market appeal, say, in Japan or Canada, they'll need broader compliance.
Right. So satisfying FMVSS 103 for windshield defrosting is necessary for those mass market aspirations. But on top of that, certain North American markets, especially the hot Southwest U.S., demand very specific cooling curves.
Right, the Death Valley test cases.
Exactly. Our sources highlight the need to specify performance under extreme conditions. For example, a 45 degrees C ambient temperature with a high solar load of 1,000 William or so, that's a huge amount of incoming radiation just cooking the cabin. This requirement is what dictates the minimum displacement and the speed capability of your electric compressor.
So if we synthesize all of this regulation into concrete engineering parameters, the real foundation of our SOR, what are the non-negotiables? What forms that base safety layer?
Okay. Based on this global convergence that's being driven by safety, our recommended minimum design targets for Section 1 of the SR are these. First, 2 hours of flame resistance. That means requiring V0 rated materials that self-extinguish quickly and don't contribute to fire propagation. Second, mandatory system compatibility with the low GWP refrigerant R1234C. And third, a base heating power, which we'll have to validate with modeling, but it's likely going to be greater than 1.8 kilowatt to reliably meet that demanding negative 18 degrees C, 20-minute EU defrost requirement.
So those 3 parameters set the floor.
They set the floor. Everything else builds on top of that.
That sets the regulatory floor. It defines the absolute safety baseline. So now, for part 2, benchmarking the market. To be strategically competitive, we can't just follow the rules. We have to ruthlessly analyze the trade-offs our competitors have already made. This is where we learn how to actually balance cost and features.
And as chief systems engineers, our strategic analysis shows the micro-EV market has really polarized into 2 key factions. You have the passive cooling faction, which is driven purely by cost minimization and BEM reduction.
And the other side.
The active management faction, which is driven by maximizing the usable range and, crucially, the charging efficiency.
So let's look at the extreme end of that passive faction, the Wuling Hongguang Mini EV. This car is a global phenomenon, and it's because of its radical minimalism. It's almost a business model disguised as a car.
That's the key insight. The Mini EV's strategy is a masterclass in just good enough engineering, and it's all dictated by the price point. In its early versions, the battery thermal management relied purely on natural convection.
Just air.
Just air, or simple forced air cooling. They were betting heavily on the inherent thermal stability of the lithium iron phosphate LFP cell chemistry and just using large air gaps between cells to passively manage the heat.
From a cost perspective, that's a massive win, right? You're eliminating the most complex thermal components from the car.
Absolutely. You eliminate the pumps, the complex pipes, the coolant reservoirs, the expensive cold plates. You're potentially saving hundreds of dollars per vehicle. But, and this is a huge but, the engineering trade-off is equally massive, and we have to document it in our SR analysis. This design severely limits the vehicle's fast charging capability. It restricts peak performance, and it requires major range penalties in extreme cold or heat. They only mitigate this in the higher trims by adding some battery heating films for low-temperature charging.
So the lesson is, if your market will accept 0 fast charging, you can simplify the TMS drastically.
Drastically. And their cabin strategy is just as Spartan.
Right.
They standardize the simplest, cheapest heating element, the high-voltage air PTC heater. And critically, air conditioning is often entirely absent in the lowest specification models.
So the strategic takeaway from the Mini EV for us is that if your target demographic is purely cost-driven, HVAC comfort is the first system to be outsourced to the driver.
Open a window, use a blanket. Exactly.
Okay, moving to another minimalist, the Citroën Ami, which represents a slightly different approach to this extreme urban LSEV design.
The Ami is really designed for maximum constraint. It operates on a low-voltage 48V system with a tiny 5.5 kilowatt battery pack. And because the motor power is extremely low, only 6 kilowatt, the heat generation from the drivetrain is almost negligible.
So the battery doesn't even need active cooling.
It's entirely naturally cooled. It requires no active TMS whatsoever.
And this presents a major strategic decision for our SOR then.
Yeah.
How small is too small for active management?
Well, the Ami demonstrates that if the product focus is strictly low power, low speed urban mobility, the last 5 kilometers, then we can eliminate the entire high cost, high complexity compressor-based AC cooling system.
Which saves a lot of money.
The Ami only uses a basic PTC heating fan, and that's primarily for defogging and just a tiny bit of heat. This can drastically reduce the bill of materials. However, if our LSEV is intended for highway speeds, even brief ones, or if it needs fast charging, this approach immediately fails all the safety and performance tests.
Right. Now let's look at a player that prioritizes efficiency and feature integration, the Toyota C+pod. Toyota is bringing its deep hybrid experience into the micro segment here.
The C+pod is fascinating. It uses active air cooling, so it's channeling conditioned cabin air through its 9.06 kilowatt battery pack. But the crucial SOR lesson here isn't the air cooling method itself, it's the choice of cabin comfort components. The C+pod includes heated seats.
I know this is one of your favorite strategic takeaways. Why are heated seats such a critical, non-obvious efficiency enhancement for an LSEV?
It's pure physics applied to a constrained environment. Most cabin heat comes from convective heating. A PTC heater is just blasting hot air, which is a poor heat transfer medium, into a large volume, the cabin. This draws massive power. We're talking 1,500 watts or more, especially when you're trying to satisfy those cold start defrost requirements.
Cool.
Heated seats, on the other hand, they rely on conductive heating. They directly warm the occupant's body, and they only draw about 100 watts per seat.
So if the cabin is still a little bit cool, but the occupants themselves are warm, you've just cut your heating energy draw by more than 90%.
Exactly. Our SRR should include heated seats as standard, regardless of trim level. This component inclusion is a really cost-effective efficiency enhancement that dramatically cuts the high winter range reduction that's caused by that massive high-voltage PTC draw.
So it transforms a simple comfort feature into a core thermal management strategy.
That's a perfect way to put it.
Finally, we have the Microlino 2.0. This vehicle, it's a high-end microcar, so it gives us a validated hard engineering number.
It does. The Microlino sets a crucial and very specific benchmark by standardizing a 1.8 kilowatt PTC heater. This data point confirms the minimum installed power that you need to meet the stringent EU defrosting requirements and still provide basic comfort in a premium two-seater micro vehicle.
And our regulatory analysis already suggested a number greater than 1.8 kilowatts.
It did, and the Microlino validates this commercially. So our SRR should anchor its HVAC heating power specification around this 1.8 kilowatt figure. We use it as the reference minimum for our simulation.
That's a great transition. We've established the safety mandate, and we've analyzed the strategic trade-offs of the competition. Okay, here's where we move into the architectural decision-making. We've established that pure air cooling simply cannot meet that 2-hour safety rule mandated by the global pace setter, GB 38031. So we need complexity, but it has to be managed complexity.
That's the engineering challenge right there. How to integrate complexity without inflating the Balaam to an unsustainable level. For a globally competitive LSEV that supports fast charging and meets these rigorous safety standards, we have to recommend a balanced modular hybrid strategy.
And what do you call that?
We call it the liquid-cooled battery plus PTC cabin heating plus motor waste heat recovery architecture. This is the optimal structure that simultaneously balances safety, performance, efficiency, and cost.
Okay, let's define the topology. It sounds like 3 distinct but strategically linked thermal loops. Let's start with loop 1, the battery liquid cooling loop, which you've said is now mandatory for safety.
This is the core safety loop. The medium is a low conductivity coolant, typically a 50-50 water-glycol mixture. The components must include a 12V electronic water pump, or EWP, an integrated cold plate that serves both cooling and structural functions.
The dual purpose we talked about.
The dual purpose, exactly. Then a chiller, which acts as the heat exchanger between the battery coolant and the refrigerant loop, and a high voltage heater, or liquid PTC, for fast preheating in cold weather. The cold plate's structural integrity has to be explicitly defined in the SOR to meet those GB 38031 bottom impact requirements.
Okay, loop 2 handles the powertrain, the electric drive unit, or EDU. Why must this loop be connected to the battery loop?
Loop 2 is dedicated to cooling the high power components, the motor stator and rotor and the inverter's power electronics, the IGBTs, or if we use them, silicon carbide, CCASI modules, which generate less heat but are more temperature sensitive.
So why the connection?
The critical strategic requirement is the plumbing connection. This loop must integrate with the battery loop, loop 1, via a temperature-controlled 3-way or 4-way mixing valve.
And that connection is what enables the strategic innovation, waste heat recovery, the so-called zero-cost heat source.
Exactly. This is where system intelligence really pays off. The motor, particularly during a hill climb or sustained driving, it generates significant waste heat. It often raises the coolant temperature above 60 degrees C.
Which is just wasted energy otherwise.
It's just dumped into the atmosphere. The control strategy that we mandate in the SOR must leverage this free heat by channeling it directly into the battery loop in cold weather. It's an elegant way to minimize reliance on that power-intensive high-voltage heater, saving precious battery energy and cutting the winter range penalty, all without adding any major component costs.
Okay, finally, loop 3 manages the cabin and the core refrigerant system. What are the key interfaces here?
This loop manages passenger comfort. Its core components are the electric compressor, the exterior condenser, the cabin evaporator, and the electronic expansion valve, or EEV. Crucially, this loop also connects to the battery chiller to extract heat from loop 1 when the battery needs cooling, like during fast charging or in hot ambient operation.
We briefly touched on the cabin heating decision, high voltage air PTC versus the heat pump. Now, given that heat pumps offer better efficiency, especially in mild colds, why are we specifying the simpler PTC for this LSEV SR?
This is a classic LSEV strategic trade-off, and it's driven entirely by that razor-thin margin. While a sophisticated heat pump can offer a coefficient of performance, a COP of 2 or 3 in mild temperatures.
Meaning it moves 2 or 3 units of heat energy for every 1 unit of electrical energy it consumes.
Right, but the complexity kills the business case.
Can you break down that cost increase for us? Why is it so prohibitive for this specific segment?
Well, the heat pump requires multiple additional components. You need extra reversing valves, reservoirs, accumulators, and significantly more complex control logic and sensors. Our analysis shows this adds between $150 and $300 to the bill of materials per vehicle.
Which is huge for a car that might only cost a few $1,000s.
Exactly. For the cost-sensitive LSEV segment, this added expense is often uneconomical. It's really difficult to justify through lifetime energy savings, unless, the vehicle is explicitly targeting regions with prolonged, mild cold where those efficiency gains are maximized.
So the PTC is just a better business decision.
The high-voltage air PTC is simpler, it's cheaper, it provides heat faster, and the cost difference is just too large. The added complexity of the heat pump just doesn't deliver the necessary return on investment for a cost-optimized vehicle, so we specify the simpler, direct PTC.
We've moved from the strategic architectural choice now to the hard numbers. This is the bedrock of a good consultancy blueprint. You have to transition from strategy to specific, measurable, and quantifiable engineering requirements.
That's right.
A successful SOR has to provide clear, actionable metrics for the team.
Exactly. The engineering team needs unambiguous targets for verification and testing. So let's start with the Battery Thermal Management System, or BTMS, SOR mandates. The primary design goal here is maintaining the cell temperature in that sweet spot of 15 degrees C to 35 degrees C.
And that's to optimize the chemistry and the longevity of the cells.
Yes, and fundamentally to ensure thermal runaway suppression.
So what are the quantifiable metrics for cooling capacity in, say, summer operation?
We have to define the upper operational limits. So we mandate that the system must support 1C continuous discharge, meaning the battery can safely supply its rated current for 1 hour, constantly or 1.5C fast charging.
Which means it can draw current 50% faster than its 1-hour rating.
Correct. And it has to do that in high ambient temperatures of 40 degrees C. To ensure the battery's health, the quantifiable thermal metrics are critical. The maximum cell temperature, Tmax, must not exceed 45 degrees C under any operational condition. Anything over 45 degrees C and you start to drastically accelerate degradation.
And you also need uniformity across the entire pack. This is where the fluid dynamics really come into play.
Correct. Uneven temperatures cause inconsistent cell aging. That rapidly reduces the pack's overall lifespan and its performance. So the maximum temperature difference across the pack, what we call delta T pack, must be strictly controlled to under 5 degrees C. The liquid cooling loop is specifically designed to achieve that narrow window.
Given the really constrained packaging space of an LSEV, how do we specify the flow requirements to guarantee that thermal uniformity?
We define the necessary fluid specifications. The coolant flow rate must be designed for a range of 10 to 20 liters per minute. Now, that high flow is necessary precisely because LSEV packaging forces tight, sometimes tortuous piping runs, which increases resistance.
You need more power to push the fluid through.
Exactly. And we mandate that the flow resistance across the entire cold plate assembly must be less than 30 kPr to ensure our chosen pump can maintain that minimum flow rate efficiently. This number is non-negotiable for the system to perform.
Okay, now heating capacity for cold climates. We've established it's necessary not just for comfort, but to actually enable safe charging.
Right. The SRR must mandate the system's ability to raise the battery temperature from a frozen starting point, specifically not at 20 degrees C up to 0 degrees C. That's the temperature threshold that usually enables safe DC fast charging.
And it has to do that within a specific time.
Within a critical time window of 30 to 45 minutes, this demands an installed power of 2 to 3 kilowatts, delivered either through the HV liquid PTC or preferably via that pre-diverted motor waste heat we talked about.
And the final line of defense against thermal runaway, circling back to that 2-hour safety rule.
We must mandate the use of directional blast valves. These are pressure relief mechanisms that are designed to rupture to vent hot gas during a catastrophic cell failure. The SRR needs a precisely calculated opening pressure, we'll call it 60 ppa, determined during the physical pack design, and it must explicitly require CFD verification that the vented gas is directed safely down and away from the passenger cabin air intakes.
A critical engineering safety clause.
Absolutely.
Moving to the cabin HVAC. What are the hard numbers there for comfort and compliance?
We specify the use of a high-voltage air PTC, and we must explicitly reject 12E low-voltage PTC.
Why is that?
Because they draw massive current, we're talking hundreds of amps. That increases your wiring harness weight and your electrical losses. It's a strategic disaster for an LSEV. The required power range is specified from 1.5 kilowatts to 2.5 kilowatters. We use the Microlino's 1.8 kilowatters as our validated minimum, but the final number has to be confirmed by a rigorous cabin thermal model simulation.
And that simulation must prove we meet the regulatory requirement.
Absolutely. The heating compliance clause in the SOR must explicitly state that the system meets the EU 672/2010 requirement for 80% defrosting clearance in 20 minutes at -18 degrees C. That's the measurable metric the design team will physically test against during validation.
And for cooling performance in those highly competitive hot markets like the U.S. Southwest?
We need a defined, challenging target. The requirement is for high-temperature operation. After the vehicle has undergone a static solar soak, so it's parked under intense sun, 35 degrees C ambient, 1,000 Willaruma solar load, the HVAC system must be able to reduce the driver's head temperature to 25 degrees C within 15 minutes of turning on the AC.
That sounds like a challenging target in a small cabin that acts like a greenhouse.
It is, and that's what dictates the required performance for the electric compressor.
So what do we spec for that?
We specify an electric scroll compressor compatible with R1234 WAFE. Based on those cooling performance requirements from the solar soak test, the estimated displacement needs to be in the range of 18 to 22 cubic centimeters per revolution. This gives the Tier 1 supplier a clear manufacturing target.
And critically, how do we manage the conflict between comfort and range in the software logic?
The SOR must define an eco mode logic. This is essential user control for the LSEV driver who's concerned about range. In this mode, the control system must immediately limit the compressor speed and significantly reduce the PTC power, say, by 50% to prioritize essential safety functions like demisting for visibility over full cabin temperature regulation.
So you're giving the user immediate, tangible control over their energy budget.
That's the goal.
Okay, finally, let's define the cooling requirements for the electric drive unit, the EDU, in Loop 2.
The primary trade-off here is between cost and power density. For most LSEV motors where the power density is below, say, 1.5 kilowatts per kilogram, the simple water jacket cooling system is the most cost-optimal solution. It relies on mature, inexpensive casting processes.
But what if you need more performance or a smaller package?
Right. If the engineering mandate requires extreme miniaturization or very high continuous power, we have to strategically consider oil cooling. While oil cooling is more expensive, its superior heat transfer efficiency can potentially shrink the motor volume by up to 50%. This becomes a strategic boom-in decision based purely on your packaging constraints.
And the pump itself. It has to be efficient and reliable.
Oh, absolutely. We specify a 12V brushless DC, or BLDC, centrifugal pump. And since this component runs almost constantly, it is the heart of the TMS. The SOR must demand a minimum lifespan of greater than 30,000 hours.
And the control.
Crucially, the control mechanism must support pulse width modulation, PWM, or LIN bus modulation. This is the strategic software control that allows for dynamic flow rate adjustment based on real-time motor and battery temperature. It ensures the pump only uses the energy that's strictly necessary, optimizing your low-load consumption.
So we've built the strategy, we've defined the architecture, and we've mandated the hard metrics. Part 5 is about executing that vision, making the right component choices in the supply chain, and integrating the software intelligence that transforms a pile of hardware into a high-performance, efficient system.
This stage requires balancing vehicle-grade reliability, and that means a 10-year service life with the aggressive consumer-grade cost targets that are inherent to the LSEV market.
Let's look at that expansion valve trade-off again. You strongly advise against the cheaper thermostatic expansion valve, the TXV, in favor of the electronic expansion valve, the EEV. Now, this adds complexity and cost. How do we justify that strategically?
The justification is range and system longevity. While the TXV is cheaper and it's purely mechanical, the SRR must mandate the electronic expansion valve, EV,
Wow.
because the EEV provides far more precise superheat control.
And what does superheat control mean for the non-engineer listening?
Think of it as protecting the most expensive part of the system, the electric compressor. If the refrigerant entering the compressor is still partially liquid, if it has low superheat, that liquid can damage the compressor valves, and that leads to catastrophic failure.
I see.
Precise EEV control ensures the refrigerant entering the compressor is always 100% superheated vapor. This maximizes efficiency and protects that high-cost component. And in an LSEV, the TMS is frequently juggling concurrent tasks, battery chilling, and cabin cooling. The EEV is the only way to efficiently modulate the refrigerant flow across both the chiller and the cabin evaporator simultaneously. It prevents performance bottlenecks and maximizes the system's overall coefficient of performance.
So we spend a little bit extra on the EEV to protect the much more expensive compressor and to maximize range. It's a classic strategic investment.
Yeah.
And which suppliers are mature enough to meet these cost targets?
We'd recommend targeting mature, high-volume suppliers like Sanhua or Yinlin. They really dominate the new energy vehicle thermal management space, and they offer the necessary cost control and reliability that's required for this high-volume, cost-sensitive LSEV segment.
Let's revisit the critical challenge of noise, vibration, and harshness, or NVH, specifically concerning the electric compressor. Why is this more difficult in a micro EV than in a larger battery electric vehicle?
It's the absence of the engine masking effect. In a large vehicle, the engine noise masks the high-frequency whine of all the auxiliary components. In a silent EV, especially a small LSEV with minimal sound dampening, the high-frequency whine of the electric compressor can be extremely noticeable and irritating to the driver. It becomes a massive quality issue.
So what do you do?
The SRR has to set a stringent NVH limit for the compressor, something like a maximum sound pressure level of less than 65 dBA at 3,000 RPM, measured at 1 meter. This is a critical quality metric for supplier selection.
Okay, now let's talk about the intelligence layer, the software. Our sources suggest that without smart control, winter range reduction can be a crippling 30 to 50%. Where does the software win that efficiency battle?
It starts with the waste heat logic. The SOR must mandate the use of those 3- or 4-way valves, controlled by the TMS, to actively divert that motor waste heat, often 60 degrees C or higher, to the battery pack during cold operation. This powerful logic ensures the battery reaches its optimal charging temperature quickly without drawing significant energy from the main HV battery.
And addressing the user experience through intelligent preconditioning is crucial for range confidence.
Yes, the SRR must mandate a sophisticated preconditioning system. This means the TMS controller needs to integrate a time departure function. When the vehicle is plugged into the grid, the controller should calculate the ambient temperature, the desired departure time, and the necessary time to warm or cool the cabin and battery to their target temperatures.
And crucially, it has to use grid power.
It must be programmed to strictly use grid power, not battery energy, for this conditioning. This ensures the user starts their journey with a comfortable cabin and a fully conditioned battery, so they retain 100% of their intended driving range.
Finally, the software's ultimate safety function, active thermal runaway suppression, which is what fulfills that 2-hour rule.
This is the critical software logic. The SOR must detail the emergency mode logic. If the battery management system, the BMS, detects a rapid, uncontrollable temperature rise, for example, greater than 10 degrees C per second in a single cell, the TMS has to immediately enter maximum operation.
What does that look like?
That means full-speed water pumps, fans at maximum volume, and maximum compressor power, all channeled through the chiller. The goal is simple: to aggressively suppress thermal propagation, to rapidly cool the liquid coolant, and to buy the occupants the critical escape time necessary to safely exit the vehicle. That's how you fulfill the 2-hour safety mandate. Right. So to synthesize this entire strategic blueprint, the thermal management system challenge for the micro LSEV is fundamentally defined by balancing 3 competing high-pressure priorities. You have absolute safety, which is driven by that 2-hour rule. You have maximum efficiency, achieved through liquid cooling and waste heat recovery. And you have aggressive cost control, which is met through the intelligent selection of standardized high-volume components.
If I summarize this strategic architecture, the engineering leverage seems to come not from inventing new technology, but from strategically optimizing existing mature systems. This deep dive really transitions the engineering team from the conceptual phase into practical, immediate development. So what are the 3 non-negotiable, immediate next steps the engineering team has to execute to move this SOR into production reality.
Okay, first, they must immediately execute a 1D thermal simulation using powerful tools like GT Suite or MSIM. This simulation has to confirm that our specified 2 kW PTC power range reliably meets that critical MEDIC 18 degrees C, 20-minute European defrost requirement. This validates our most energy-intensive specifications.
Second, validating the core safety feature.
Correct. We must work directly with the chosen battery supplier to verify their cell thermal runaway data in conjunction with our liquid cold plate support. This data is essential for the definitive decision on whether we need supplemental high-performance passive materials, like aerogel insulation pads, to guarantee compliance with that 2-hour no propagation rule under all conditions. This is the final safety sign-off.
And third, locking in the supply base based on these strict metrics.
The team must issue a detailed request for information, an RFI, to Tier 1 suppliers. This RFI has to be based directly on the strict component specifications and quantifiable metrics, the flow rates, the temperature deltas, the NVH limits, and the EEV requirements that we've defined in this SOR. This locks in the required quality and performance targets before we ever move to costly physical prototype development.
We started by calling this an engineering gambit, and this strategic analysis proves it. It's a comprehensive technical blueprint delivered under immense financial and spatial constraints.
And here's a final provocative thought for you to consider. This detailed SOR shows that success in the micro-EV segment isn't really about breakthrough component invention. It's about ruthless strategic optimization. The crucial engineering decision isn't the choice of refrigerant or pump. It's the decision to rely heavily on the mature, cost-competitive suppliers that are dominating the global supply chain, particularly those based in Asia.
So the supply chain decision is the real leverage point.
That supply chain decision dictates whether the vehicle can even hit the required market price point while remaining perfectly safe and compliant with that stringent 2-hour rule. That is where the ultimate system engineering leverage truly lies.
That structural insight that the supply chain strategy is actually more powerful than the technical spec is a fantastic place to leave this deep dive. Thank you for guiding us through engineering the invisible, yet absolutely essential, core of the micro-EV.